Notice you have seen that before, and this. We continue with formulae from section C, sound and light. We already completed these three here, 1, 2, and 3. Now we continue with this fourth one, which says that magnification is equal to image height over object height. And this is calculating the magnification based on the height of the image and the height of the object. M, of course, is magnification of the image when compared with the object, and it has no unit as it is a ratio. Example 1. An object is 11 centimeters tall. Its image formed by a convex lens is 22 centimeters in height. What is the magnification of the image? Now, this is fairly simple. If the object is 11 centimeters and the image is 22 centimeters, then you can clearly see that the image is twice as tall as the object. But let us use the formula to get accustomed to using this formula. We write object height, 11 centimeters, image height, 22 centimeters, magnification. We know that magnification is equal to image height divided by object height. And so we divide 22 centimeters by 11 centimeters, and we get 2.0. Correct the two significant figures. Normally, you would see that written as times 2.0. That is to say, the image is 2 times as tall as the object. Or you could state it like this if you want to be more precise. So that is example 1 in using formula 4. We look now at example 2. An object is 22 centimeters tall. Its image formed by a concave lens is 11 centimeters in height. What is the magnification of the image? Well, we know the object height is 22 centimeters. We know the image height is 11 centimeters. We want to find the magnification. Well, magnification is equal to image height divided by object height. And so we divide 11 by 22, and we get magnification as 0.50, normally written as times 0.5. That is to say, the image is 1/2 as tall as the object. We can write it like that to be more precise. Now note, in this case, the image is actually smaller than the object. It is less than times 1. But that is still said to be its magnification. Example 3, you need to magnify an object 8.0 times so that its image is 32 centimeters tall. What must the height of that object be? So what do we know? We know that the image height needs to be 32 centimeters and that the magnification is 8.0. We want to find the object height. So magnification is equal to image height over object height. We change that formula around to make object height the subject. So object height would be image height divided by magnification. And we get 32 centimeters divided by 8. And so the object height needs to be 4.0 centimeters, corrected to significant figures as we are using here. If we want to be more precise, we could say 4.0 plus or minus 0.0 0.05 centimeters. In those three examples, we were looking at magnification in terms of image and object height. Now we will look at magnification in terms of image distance and object distance. Now this formula deals with magnification of an image based on distance of the image and the object. M, of course, is magnification of the image when compared to the object. It is a ratio, so it has no units. We will return to this formula after we clearly understand what these quantities are. Let us say you have a convex lens like that, and we draw a line straight through its center going across. That line is called the principal axis. On this side, we will locate a point called the principal focus, which is F1. And the other side has a similar point called F2. Now, if we double the distance of that F1, we will get 2F1. And the same thing applies over on this side, 2F2. If we put an object at this point between the principal focus and twice the principal focus on the left-hand side, now let's remove this lens and just put a line there so we can more clearly see what is happening. The distance from the object to the center of the lens is called the object distance. That is U in this formula up here. If we draw a ray from the top of this object parallel to the principal axis, it will pass through the principal focus on this side. And if we draw another ray that goes straight through this point, those two rays will meet at this point over here, and we will get an image, a real image. The distance from the image to the lens is called the image distance, of course, and that is given the symbol V. So now we know what is object distance and what is image distance. So we can now go and use this formula here comfortably. By the way, to get that image there, you could draw a third ray that goes through this principal focus on this side, touches the lens, but then it comes out parallel here. In any case, all three of those rays will meet at the same point to give us that image. In drawing ray diagram, you do not need to draw all three of those rays. All you need would be two of them. All right, so let's get back to the formula. Example 4. If the image distance is 51 centimeters by a convex lens, and the object distance is 20.0 centimeters, what is the magnification of the image? So we know that V is equal to 21 centimeters, U is equal to 20 centimeters. We want to find M. We know M is equal to V over U, that is to say, image distance over object distance. And we substitute the numbers we are given, and we get a magnification of 2.6, rounded off to two significant figures. Let's look at another example. If the object distance is 15 centimeters and its magnification is 4.5, calculate the image distance if said image is formed by a convex. So what do we know? We know the object distance is 15 centimeters. We know the magnification is 4.5, and we want to find the image distance. M is equal to V over U. We want to find V, which is equal to M times U. We substitute the numbers we are given, and we get an answer of 68 centimeters. This is correct too, but I think that will suffice for CSEC. If you want to be a little more precise, you can always write that. 68 plus or minus 0.5. centimeters. But this should be sufficient for CSEC. We now turn our attention to Formula 5. But before we get there, we need to understand what the term focal length means. Let's go back to that convex lens we had before. If we were to draw a line going straight through its center, that imaginary line is called the principal axis. Let's remove that lens so we can more clearly see what is happening. If we draw a ray parallel to the principal axis over on this side, that ray must pass through the principal focus on the other side. Here, if you draw another ray, it will also pass through that point. And any other ray on the left-hand side that is parallel to this principal axis will pass through that same point. Now, this point here has a special name, and it is called the principal focus, labeled F1. Of course, if those rays were coming from the right-hand side towards the left, you would have a similar point, which is called F2 on the other side. Let's go back to the rays coming from the left-hand side to the principal focus at F1. If you imagine a piece of board, like a plyboard, facing that lens upright like this, that imaginary surface has a special name, and it is called the focal plane. In other words, any ray that comes through here, 2 or 3 rays from the left-hand side, must come to focus on that focal plane. Now, the distance from the focal plane to the lens is given the symbol F, and that means the focal length. So now let's get back to the formula. 1 over F is equal to 1 over U plus 1 over V. That is to say, 1 over the focal length is equal to 1 over the object distance plus 1 over the image. As we know, F stands for the focal length, U is the object distance, and V is the image distance. So now let's look at the first example for this Formula 5. Calculate the focal length of a convex lens if the image distance is 15.0 centimeters and the object distance is 6.0 centimeters. We know the image distance, we know the object distance, we want to find F. We know that 1 over F is equal to 1 over U plus 1 over V. So let's substitute the numbers we are given, and we solve this part, and we get 1 over F is equal to 7 over 30. Let's invert both sides of the equation, so we get F over 1, which is really F, is equal to 30 over 7, which works out to be that, and we round it off to 2 significant figures, and we get 4.3 centimeters. So the focal length is 4.3 centimeters. This is also correct, but we will stay with that version, and even better would be this one, 4.3 plus or minus 0.05 centimeters. Let's look at example 2 for this Formula 5. Calculate the image distance for a convex lens if its focal length is 65 millimeters and its object distance is 72 millimeters. So we know the focal length is 65 millimeters. We know the object distance is 72 millimeters. We want to find the image distance. We have a formula here that says 1 over F is equal to 1 over U plus 1 over v. If we change this around somewhat, then we get 1 over v is equal to 1 over f minus 1 over u. We substitute the numbers we are given, and we get 1 over v is equal to 7 over 4680 millimeters. Now let's invert both sides of the equation, and we get v is equal to 4680 over 7. Work that out, and we get this rounded off to 2 significant figures. So the image distance will be 670 millimeters. If we want, we could be a little more precise with that, but this should suffice for CSEC. That is also correct, but CXC prefers this version. Example 3. Calculate the image distance for a convex lens if its focal length is 68 millimeters and its object distance is 58 millimeters. All right, so that represents our convex lens. This is our principal axis. Here is F1, that is F2. It says here that the focal length is 68 millimeters. It further says that the object distance is 58 millimeters. That is to say, this is the object. So note that the object is within the focal length. Because you have 2f1 on this side here and 2f2 on that side there. If we draw a ray from the top of the object parallel to the principal axis until it touches this convex lens, we know that that ray must pass through the principal focus on this side, like that. And if we take a ray going straight through this point here, from the top of this object, you notice what is happening. These two rays are diverging from one another. They are not going to meet to form an image. So what we do in that case, we project those two rays backwards, so that that first ray, we project it back that way, and this one, we project it that way, and notice they meet at this point. And so we have an image that looks like this. Notice it is not drawn in a solid line, so it's not a real image. It's actually a virtual image. And what we are doing here is using that lens as a magnifying glass. As long as the object is within the principal focus, then the image will always be magnified, virtual, and upright, as you see here. So if you understand that, when we work this out, you will not be surprised at the answer. This distance here is the image distance, and this is what we want to find. So let's get back to the question. So we know that the focal length is 68 millimeters and the object distance is 58 millimeters. So focal length, object distance. We want to find image distance. We have this formula here that says 1 over f is equal to 1 over u plus 1 over v. We change the formula around so that 1 over v is now the subject. We substitute the numbers that we have, and we get 1 over v is equal to this. Now remember, that is not v, that is 1 over v. If we invert both sides of this equation, then we get v over 1, which is really v, is equal to 1972 divided by negative 5, which gives us this answer here, and we get negative 394.4 millimeters. Notice though that we have dropped the negative here. So let me explain that. This negative means that the image is virtual. It is dropped in the final answer. So we calculated that the image distance is negative 394.4 millimeters, which really means a virtual image of positive 390 rounded off to two significant figures. So anytime you do a question like this, check to see if the object is within the principal focus. And that's it for section C, where we were dealing with waves, and that would be sound wave and light waves. We next move on to section D, which is electricity and magnetism. And these are the 7 formulae, 7 really. This one here is a combination of formula 2 and 3. And that would be the formulae that we have to do for electricity and magnetism, which we will begin to do in the next video. This brings us to the end of this video, Physics 17.